Oh, guess everybody should qualify. Yeah.
Okay, good afternoon, everybody. This is the 2019 fall semester WRS seminar. And our speaker today is Dr. John Nieber from the Department of Bioproducts and Biosystems Engineering. He's going to talk about water storage in Minnesota. John received his PhD from Cornell University, and then he started working here as a professor in the Department of Bioproducts and Biosystems Engineering, as is known today, 1985, I believe. And he's also the Director of Graduate Studies for the Water Resources Science Program. So with that, John, take it away.
Thank you, Dave. Appreciate people coming today. Nice, we don't have a really nice day outside. Everyone might choose to be out there. This time of year, you can actually really nice weather. What I'm going to speak about today is a project that I've been working on for the past couple of years about attempting to use different methods to quantify how much water is stored in the landscape. And here we're not talking about just surface water, but also soil moisture, groundwater, water in lakes, water in wetlands, water in rivers, and so forth. And be able to do this in a using different data sources. I've listed on here the research team, includes Dr. Bruce Wilson, Carrie Holmberg, Francisco LaHoo, from the Bioproducts and Biosystems Engineering Department, and then 3 graduate students from Water Resource Science, Chelsea Delaney, Victor Tang, and Jiang Li. And then Jared Trost is a collaborator from the U.S. Geological Survey. The project was funded by the Legislative Commission on Minnesota Resources. The project started in July of 2017. And other collaborators on the project were Dr. Tim Griffiths and Dr. John Baker from the Soil, Water, and Climate Department. Adam Heathcote from the Minnesota Science Museum, and Chuck Regan from the Minnesota Pollution Control Agency. And I want to also recognize Lynn Bergquist and Andy Wilquist from the Minnesota Department of Natural Resources, because they helped us with getting some lake bathymetry data that was used in quantifying lake volume. So to start this off, I put up the famous Minnesota license plate. You know, we're kind of reminded all the time of our relationship with water here in Minnesota, the land of 10,000 lakes. And I had to add something to that because there's actually greater than 10,000 lakes. And everybody knows that, but maybe not everybody knows how many more than 10,000 that there is. And it's not just the lakes, but we also have plentiful water. There's a lot more groundwater than there is lake water. But we do know about all those lakes, and that's something that we're reminded of every day, not only from the license plate, but just by driving around the landscape. But you know, how is it that we can quantify or know how much water there actually is, and what the effect is that we might have on that water, you know, for using it for domestic use or for industrial use, irrigation, things like that. How does that affect how much water we actually have stored in the landscape? That's something that is the focus of the study that we're doing. So I've already mentioned, you know, Minnesota does have a great deal of water. Here's a cross section maybe of a representative area in Minnesota where we've got bedrock, and on top of that you've got some sort of glacial sediments that are deposited, and within that we've got saturated zone, which is indicated by the blue area that's of the material, and then on top of that there's the unsaturated material, which would be the soil material. And we have wetlands, we have lakes and rivers in the cross section. And so this would be a representation of the landscape that we might see in Minnesota, and does represent that, again, that we have a great deal of water in the landscape. But, some changes can, in water use, increase in water use can have some detrimental effects, such that if we were to drop that saturated zone enough, its connection with the surface water can be affected, and this then might dry up wetlands, decrease the amount of water that be in wetlands and streams, and also affect some lakes. And I think this is, of course, been on people's mind about trying to avoid these types of problems. On the left, you see an example where a river, a river that flows very well, the Little Clover River in central Wisconsin, a picture of it in 1997, and then in 2005. So this was attributed, the cause of this was attributed to over-irrigation in the area. And on the right-hand side, we have the well-known White Bear Lake case, where you can see where the water line was in 2004, and then it steadily dropped. And this is in 2010. Well, we're in 2019 now, and things have been reversing. Water levels have been going up, and of course, these things happen naturally. But again, there was an attribution of this being caused by over pumping of groundwater. The close connection between the lake and the groundwater is affecting the water levels in the lake. So those are the kind of problems that we'd like to be able to avoid. Well, we do spend a lot of time, a lot of money on trying to monitor how much water we have, what the fluxes of water are, and how much water there is. So I've got on this diagram some illustrations of different types of monitoring instruments. And there might be monitoring wells that are in the bedrock, measuring a piezometric surface within that, or a monitoring well in the quaternary material or this glacial material, and then stream gauges, staff gauges, and lakes that can, if they're monitored, then you can quantify, at least at that point where it's monitored, how much water happens to be stored in that particular terrestrial element of the landscape. Question comes up about how well do those measurements represent the big picture. So if we have, just for instance, here the same diagram, but we have just one monitoring well, what does that say about the amount of water that's stored? If I were to show you a picture of how many monitoring wells are across the state, it's not very many. And you'd see, maybe on the map it looked like there's a lot, but when you look how much distance there is between these monitoring wells, it could leave you aghast at trying to figure out how much water is actually stored based just on a monitoring well. So can we say much about the change in storage just based on water level measurements at this one monitoring well? And what if, for instance, there's a high capacity well that's put in near this monitoring well? It might affect the water level very locally, but does that mean that there's a large change in storage in this watershed in this area just based on that one measurement? And I think if you look at the diagram, it would indicate that it's not going to, that one monitoring well is not going to represent the change in storage very well over the whole landscape. So there are these three approaches that I'll mention about how to estimate storage change. One is based on using ground-based data. And of course, as I've shown already, these provide point-wise measurements of storage. You take the information and calculate storage from that. This, of course, is costly. It requires a lot of dedication and time, as well as money, to be able to maintain and process those data. And in many cases, you might put in monitoring sites that are duplicative of other sites, and so then you may not get additional information from additional locations. A second way to do it, and this is relatively simple and fairly inexpensive, is to use hydrologic models. Basically you have inputs and outputs from those hydrologic models. You put in rainfall, you take out ET, you take out discharge, you have percolation and things like that. And these can be used, or they'll generally, if they're done properly, can calculate the change in storage in different elements of the landscape. Problem with that is, of course, that those models are not constrained based, to the numbers that they give. You've got measured precip. Well, you have to depend on the accuracy of that precipitation measurement over a large area. You got ET. That's a very difficult quantity to try to estimate. And then you have discharge. Usually that's measured very accurately. But using the hydrologic model with those inputs to calculate the water storage change such that things match the discharge doesn't necessarily mean that the model is properly calibrated, because you might be off on the ET, off on the rainfall. Even if you fit things to the preset, to the discharge from the watershed, it doesn't necessarily mean that the model is properly calibrated. So quantifying the water storage could provide an additional constraint such that you can make the model do a better job of predicting hydrologic events. The third approach here would be to use remote sensing data platforms. And generally, these are going to be fairly large scale. They don't have to be, but it depends on what type of thing you're trying to sense. But these would then provide estimates on a larger aggregated scale. Accurate information is not usually distinguishable from that information, but maybe by using ground-based data with remote sensing data, you can actually get at the finer details. So the proposed approach, and this is not novel, this is a proposed approach, which a lot of people have used before, is this, using the three methods or approaches that I just talked about. And that is to use remote sensing platforms based on satellites. It doesn't have to be on satellites, but in this case, we're using satellites. Ground-based observations such as wells, stream flow, lake levels, weather measurements. And then finally, coupling that with a hydrologic model using the remote sensing information as well as the ground-based information. So that using those three, we're proposing you can get at the finer scale features as well as be able to confirm that the numbers that the measurements you're getting from the different measurements agree with each other. So the objectives of the study were to use ground-based measurements to estimate terrestrial water storage and various components such as the lakes, wetlands, soil moisture, groundwater. Here I talk about total groundwater and active groundwater, and I'll define those here. And do this for a period from 2002 to 2015. The reason I chose that time period is because one of the satellites, the gray satellite, was up and running from that during that period of time. It actually went from 2002 to 2017 until the satellite went on, went beyond its life. There's a new satellite that's been put up to replace that one. To estimate changes in storage in the water storage in the study area using the data from a remote sensing platform, that is from satellites, and then to quantify changes in water storage at the watershed scale using water balance models. So all three of those different approaches I've talked about, we've been using in this study. So just to give you an idea, the remote sensing platforms that we use for the gray satellite, which is gravity, recovery, and climate experiment, basically two satellites in tandem. They move along, they sense the difference in the gravitational field that makes them move relative to each other, and that spacing between them can be measured to one nanometer, so you can get very accurate measurements of effects of changing gravitational field. Lots of things affect the gravitational field. So NASA does a lot of processing of this data. In the end, you end up with a number for the amount of water, mass of water that's stored in the landscape. And that's the total amount. So it's all the groundwater, all the soil moisture, all the surface water. SMAP, which is a soil moisture active passive satellite, is the second. And then Landsat to be able to visualize, basically get information about surface water, lakes in this case. This is a 30-meter footprint, so you can't have lakes too small in order to be able to see something. And then for ground-based observations, there's the observation wells, stream and lake stage gauges, and then meteorological information. So we used all these features in our estimation of water storage change using the different approaches that I've talked about. Now for modeling, here's a representation of a model. This happens to be the hydrologic modeling system, HEC1. This picture here is from the watershed modeling system, which allows you to use different types of hydrologic models. This one happens to be the HEC1 model developed by the U.S. Army Corps of Engineers. And you can see it is a semi-distributed model in which the watershed is divided up into land parcels, and then runoff, groundwater flow, and so forth is calculated. Water balance is calculated for each one of these sub areas, and then coupled together in a network to provide discharge at the watershed outlet. And that's the type of model that we were striving to use in our study. We happen to be using the HSPF model. I'll explain later why we happen to be using that model. But this is a diagram that illustrates the concept that we were using in doing hydrologic modeling. So the study region that we were funded to conduct is in central Minnesota. It actually extends from Dakota County up to Moorhead, Minnesota. So it spans tributary areas to the Mississippi River as well as to the Red River of the north. There are 17 HUC-8 watersheds located within this study area. And the idea, what you see on there are some of the gauging station locations for both the major gauging stations as well as some of the minor gauging stations that are available for this area. So just to give you some results up front, we've done an analysis of the point-wise data, and I'll explain a little bit about how we did that. But first, I thought it would be worthwhile to give you just some idea what kind of numbers we have come up with. So these are the volumes of water stored for the study region. These just happen to be for a particular date in that period of time. Things do change from 2002 to 2015, but just to give you an idea as to what these numbers might be. So for groundwater, and again, this is groundwater that's above the shallowest bedrock. So it'd be just in the quaternary material, the glacial sediments that are deposited on the surface of that bedrock. And for that, in the whole study region, which is about 53,000 square kilometers in area, the groundwater is storage is 1,500 cubic meters. I mean, we knew it was going to be a big number, but that's the figure that we obtained for this study region. Active groundwater is 33 cubic kilometers. Now, our definition of active groundwater, imagine that we're talking about the groundwater that's in connection with surface water, lakes and streams and wetlands. So if that water table drops below the bottom of any one of those features, a lake, a wetland, or a river, that water body is going to dry up. Because it requires that connection between the groundwater and the surface water. So we're still working on refining this definition. It's rather complicated. All these calculations are done with ArcGIS, and we still need to work a bit on trying to refine this active groundwater component. But you can see it's a very small number compared to the total groundwater. And one of my take-home messages later is going to be, this shows how sensitive water extraction can affect the health, let's say, of our surface waters, lakes, and wetlands and rivers. For soil moisture, 20 cubic kilometers. Lakes was 15, and wetlands is 1.5. Get an idea as to what kind of numbers we'll be seeing later. Yes, right?
John, what's the area of your study area?
It's 53,000 53,000 square kilometers. So I think it's all those 17 HUC 8 watersheds. Just a little over 53,000. All right, so to just give you an idea as to how these calculations were done for the using ground-based data, I'll talk first about the groundwater component. So here we've got a cross-section similar to the one I was showing before. So you've got the land surface, so we have a 30-meter DEM. We've got soil information. We've got aquifer, shallow aquifer information, and we know the depth of the bedrock over this entire area of our entire study area. We have an unsaturated part and a saturated part. What we do here is, well, first I'll talk just geometrically here about calculation. So the part that's unsaturated would have a certain depth to it at each of the 30 by 30 meter points, control points that we use in doing an integration over the entire study area. The unsaturated storage would be the part that's above the water table, between the water table and the soil surface. And the soil water storage, then, we tried to keep it simple. We took that depth, D1, which is the depth of the unsaturated zone, multiplied by the field capacity. Well, that might be too high sometimes, it might be too low, the field capacity, but that's the number we used in our study because soil moisture can be so dynamic. And then the active groundwater storage is this THK1. It's that multiplied by the porosity of the aquifer material. And this is our current definition of active groundwater, the distance between the actual water table level at a given time and a point that, or a depth that's 5 feet below the minimum water table level that was observed at that point during the period 2002 to 2015. I'm not saying this is finalized. This is something that we're going to be working on. Ideally, we want the bottom to be right here at the base of the stream at that location. That's something we're working on. It's a geometric challenge to try it in GIS to get this to work. And then finally, of course, the total groundwater storage would be all the way from the water table at a given date and the bedrock at that location, and that's multiplied by the porosity of the aquifer material. For this, we use monitoring wells to determine where the water table surface happens to be at a given time. That was interpolated across the landscape, and other controls would be the surface water. So whatever the level of the lakes happen to be, because here we assume that the water table is in direct connection with the water table or with the water level in a lake or in a stream. So those elevations were used to determine the location of the water table. And so then this was integrated over the entire landscape, the 30 by 30 meter grid of water table levels to do the calculation of the water storage. And in the end, we subtracted off the volume that's in the lakes because that in the integration scheme, we didn't really subtract that off in the integration scheme. So in the end, you have to subtract off the volume that's in the lakes so you're not double counting that with the groundwater. Just to give you an idea of our distribution of wells and of lakes in the region, the blue dots are the lakes that we use. There were 816 monitoring lakes, and there were 107 monitoring wells that were used in doing this. Now, it looks like there's a lot of monitoring locations here. Some of the watersheds don't have very many monitoring locations, but when you come down to it, there's a lot of distance between those monitoring locations. But the integration of the volume over this was done by doing interpolation between points, Kriging type interpolation, and then the volumes were calculated based on the water table level that was mapped from that. So groundwater storage estimates, and these are in millimeters, and this is the total groundwater storage. So for the different watersheds, the dark blue would be the ones that have the highest volume of water stored, and everything is normalized based on the watershed area. So if you take the volume that's stored in that watershed, divide it by the area of the watershed, and that gives you millimeters of water. So, you know, we're looking at 51,000 as the maximum value and 10,000 as the minimum value, or you could say 10 meters to 51 meters. And overall, the whole watershed, I indicated there was 28, well, I will indicate there's 28 meters basically on average over the whole study area. But it gives you an idea as to how that distribution of stored water is there within the study area. For soil moisture, this again varies over the entire area, and again these are expressed in millimeters depth of water. The dark blue area is between 480 and 725 millimeters. The lowest would be the green area, which is 213 to 271 millimeters. And of course, that doesn't necessarily mean a particular soil is really dry and another area is really wet. It depends on how thick the soil is. If you have a high water table, you don't have much room to have soil moisture. So some of these areas have higher water table than others. So the results from the groundwater and soil moisture storage measurements, quantification is, again, groundwater was 1,500 cubic kilometers. That's equivalent to 28 meters of water, average over the entire landscape. So that's a lot of water. Active groundwater was 33 cubic kilometers, which is equivalent to 613 millimeters of water, averaged over the entire study area. And then for soil moisture is 20 square cubic kilometers, equivalent to 373 millimeters of water. I've defined for you what is the active groundwater component. Then we did an analysis for the volume of water in lakes in this region, and here's just a picture, GIS picture showing the distribution of lakes. You can see Lake Mille Lacs right here, the large lake that's located there. You can see that the lake distribution is not uniform throughout the study region. Some places have many more lakes than others. But we were interested in being able to quantify the volume in the lakes. And something out of order here, but I wanted to talk about the methodology that was used, but I don't see that the methodology is here. Anyway, we used 3 different methods for quantifying the volume in the lakes. One was just a pure statistical method that basically took the area of the lake and related it to the volume of the lake to that area. We had 816 lakes in which we had bathymetric information so that we could calculate the volume of the lake and relate it to the area. And these dots or these plotted points on the graph are those monitored or those lakes that we got from the Department of Natural Resources. On the horizontal axis, we have the surface area. In this case, it's represented in hectares, the log of the surface area to the log of the volume in hectare meters of water. And you can see that there's some spread around the fitted line. This happens to be a breakpoint line, so the equation that's given on the graph is a breakpoint that it depends on there's a size range here. So up to a certain point, 1.5 hectares, you had one graph, and so forth as you go up towards the very largest lakes. Lake Mille Lacs is not included in here because it just basically distorts the entire graph. And, so this was the way in which we estimated lake volume based on lake area. This is fitted for the particular lakes in which we had information. We use 3 different methods. This is the pure statistical approach. We use 2 other approaches. One in which you take the area and you take the slope of the land surface along the edge of the lake to come up with the lake volume. The third method uses a self-affine method, which basically is a scaling method to come up with lake volume. All 3 methods actually yielded similar results to the one that you see here. Just to indicate the change in lake surface area as indicated by a Landsat, here's an image of one lake, basically 2 lakes. The blue area, or maybe purple area that you see on there, is the main feature of the lake in 2012. And then the, well, actually purple would be the one in 2015. The one in 2012 is the bluish area. And what this is indicating is that there was an increase in lake surface area between 2012 and 2015. In 2012, on the bottom is a graph showing the lake volume. Again, this is for the entire watershed area, or for the entire study area, expressed in millimeters. There was a drop-off in the total volume of water in the project area in 2012. We still haven't figured out why that was, but it seemed to be consistent with the GRACE data and so forth. And then there was an increase in that storage volume after that. And the dark blue circle in 2012 indicates the volume for the entire study area in all of the lakes in the entire study area in about 2012. And then the lighter colored, the purple area is the lake volume in 2015. Now, to estimate the wetland volumes, we applied data from the National Wetland Inventory. And this is not the newest inventory because that was in process of being completed while we were doing the project. So we used the older inventory to do that. We used the mapped classifications that were available in that inventory to separate volume estimates into perennial and seasonal volumes, and also to estimate the water depths. We derived error bounds based on uncertainty about water depths within those particular types of wetlands. Bogs were treated separately because there's not standing water in bogs, but the estimated volumes were included with the wetland total and not put in with groundwater, because of course bogs have a saturated material, and maybe you would put it in with groundwater, but we included that with the wetland volumes. So here's the maximum water storage limit. Again, there's a variation over time. There's a variation of water in the wetlands based on whether they're perennial or whether they're seasonal. And I'm just showing the one representation of the maximum water storage that would occur in perennial wetlands. So this would be the upper bound of what we expect that volume would be. And again, these are expressed in millimeters, and you can see again, you get appreciation for where most of the wetland storage is within the landscape. The greenish areas are the ones that have less wetland storage compared to the dark blue areas. So here again is the results for the lakes and wetlands. So for the lakes, about 280 millimeters of water over the entire project area. For wetlands, about 28 millimeters. Just point out that Lake Mille Lacs is about 18% of the total volume of water in the entire study area for lakes. And then bogs were about 10% of the total for the wetland volume. All right, so then we get down to talk a little bit about the water balance model. Now, this one is really simple water balance model. It has nothing to do with semi or distributed or anything. It just takes the whole watershed. We've got this little cartoon of a watershed with precipitation coming in, evapotranspiration going off, and then discharge coming out of the watershed. And the water balance equation is very simple. It's just the change in storage is equal to the precipitation minus the ET minus Q. So that's what the model would do. And this is a very simple model because it gives you a gross value over basically average value over the entire watershed. We could break that watershed up into smaller parts, which is what we're currently doing with the HSPF model and calculating changes in water storage in different places within the watershed. So for this, the precipitation data came from the Minnesota State Climatological Office. ET we got from the USGS CEDA, which is Center for Integrated Data Analytics. We found that those data fit best with the control data that we had at weather station sites. And then the discharge was from the USGS and from the Department of Natural Resources gauging station sites. So we get this delta S from the model. We want to get delta S. We can get it from our ground-based data because we have a time series of ground-based water storage changes, and then we can also get the delta S from the GRACE satellite. So I have a kind of a blank slide here because the time series of storage change based on ground-based data calculation, I didn't put it on here. So I had to get that put on here just to illustrate. But I wanted to put this in here as a placeholder for any future presentation I do. And I didn't ask my students to give me that graph in time to put it into the presentation. But I will talk about the GRACE satellite result here. And that is shown here. Our study area is illustrated. These rectangles that you see are the tiles, basically the footprint from the GRACE satellite. And so you can see that those footprints are much larger than the Huckgate watersheds. We took those GRACE satellite signals for each of those tiles that are covering the watersheds, the study region. And for any one of the watersheds, we could use, do some weighted average calculation storage change. So to tell you a little about the GRACE satellite, it passes over a point approximately every 30 days. The process signal, which comes from NASA, gives a measure of the total mass of water that's present on or under the land within a given tile. And this time series available from 2002 to 2015. We did, or 2017, we've done it we've used it from 2002 to 2015 in our study. So what I'm going to show is that just one example, we've used the GRACE satellite signal to look at individual watersheds, Huckgate watersheds, and done water balances on the Huckgate watershed. I'm going to show just a result for the entire study area, where the storage from the GRACE satellite used all of the tiles that you see here. And this is from 2002 to 2015. So here's the time series of storage change based on the GRACE data. And these are seasonal changes. So basically taking the seasons of the year, averaging the signal for each season, and then calculating a difference in from one season to the next. Because the GRACE signal gives you the storage at a given time. You want to know what the change in storage is between times, because that delta S from the model is a change in storage. So here, this is the seasonal average value is in millimeters per month. So that tells you how much change. You can see that it's either positive or negative, indicating that there's an increase or decrease in the storage amount. We then took that model, that very simple model, for the entire study area. So we're not looking at the distribution of storage within all those watersheds. We're just taking the precipitation that fell over the entire study area at any given time, the ET from the CEDA data, and then the discharge here at St. Paul, from the mouth of the Mississippi, not at the mouth of the Mississippi, but where the Mississippi discharges down here at St. Paul. And you can see that there's a high correlation, appears to be a high correlation between the delta S that's calculated on the model and the GRACE signal. Yeah, there are some deviations, but the R squared between them is 71%, which we consider to be fairly good. I think the Nash Sutcliffe value that we got for one of our watersheds was about 0.4, which is not so bad either. So we're taking this a step further. This fall, we're working on this semi-distributed hydrologic model, the HSPF model, which is hydrologic system modeling Fortran, being applied to the watersheds in the study region. The HSPF counts for all the different components of the hydrologic cycle. You have semi-distributed, so you break the watershed up into smaller components. So you take the Huck 8 watershed, you break it up into smaller units based on land use, based on topography, and so forth. You have surface water, you have groundwater, you have water stored in river channels, and so forth. It would be classified as being a semi-distributed hydrologic model. What we're doing is, one of the reasons we chose HSPF is because it's been calibrated for all Huck 8 watersheds in the state, and even some Huck 12 watersheds. So the MPCA has all these models available to us. So we've started to work on that, and so far we've worked a little bit with the Rum River model and also with the Wild Rice watershed model. And these is where the collaboration with Dr. Chuck Bree comes in. The model allows us to obtain actual, or to calculate spatial distribution of water storage, not just get an average over the entire watershed. So this is just an example. I think that the numbers here are not quite right yet. Victor Tang, one of the WRS students, is working on this. You can see Lake Mille Lacs up there. It's a very large, dark area. That's got the most storage, but what's shown here are the storage components. So rather than just having a lumped representation of watershed, this watershed is subdivided into different land units, and we're able to calculate the change in storage in each one of these locations within the watershed. So I'm hoping that in future presentations I'll be able to show an animation. Actually, this came out of an animation, but with results that maybe agree with measurements of changes in water storage. We know that this model is calibrated, so it does fit the discharge at the mouth of the watershed very well. But the question is whether ET that's being calculated by the model is correct, or whether the precipitation that's being applied is representative or not is another question. So take-home points that I'd like to bring out here are, again, the water stored in the groundwater. I've already mentioned these, but 1,500 cubic meters of water in there. Total groundwater, active groundwater is 33 cubic kilometers. Soil moisture is 20 cubic kilometers. Lakes are 15, and wetlands is 1.5 cubic kilometers. I'd already mentioned about the fact that groundwater surface water interaction is very sensitive to the connection between those two storage quantities. Storage entities, and because of the fact that the active groundwater, as we've defined it, is quite small, removal of some of that water, either natural or by man, can have a big impact on that connection and can interrupt that interaction. The temporal and spatial variability of estimated total terrestrial water storage obtained by the ground-based data, which I showed, just numbers, at the top of the graph here, or on the screen, you can see the numbers that we came up with, but these numbers vary over the study period, and we have those numbers. So the temporal variability of that total storage agrees well with the gray satellite data, and also I've already shown you the water balance calculations were fairly good agreement with that water storage. There are some anomalies in the gray satellite data that remain to be explained. Things where go up and the other doesn't go up as high, or maybe where balance might show a decrease when gray signal indicates an increase. Some of those things still need to be worked on. And then finally, just we're doing this additional hydrologic modeling work to not look at the entire watershed as a lumped entity, but also to try to look at the distribution of storage throughout that. And that's where we're using the HSPF model. And this is the part of the ongoing work that we have with the LCCMR study, which will end in June of 2020. And with that, see if you have any questions for me. Yes.
So you'll eventually be able to, oh, I'm sorry.
That's all right. You've started, Larry. Go ahead.
Well, I mean, eventually you'll be able to identify, because there's so little water on top, the lakes and mountains and stuff. You'll be able to identify eventually how much withdrawal, irrigation and such, you need to, where the sensitive wetland and lake areas are, that could get drawn down rather quickly if it was irrigation withdrawal or such.
Yeah.
Essentially increasing PT, essentially.
Yeah, I mean, it depends on scale here. Right now we're looking at the Huck 8 watershed scale at the best. Yeah, you've got a monitoring well out there. It might tell you what you need. I'm not saying that, the point measurements are, I'm not saying all that those are not worth something. They definitely need to have those. What I'm advocating here is for a range of ways of making the measurements and calculations, trying to tie these things together, and so hopefully we would be able to use the remote sensing information to come up with that could give you an indication what's happening in the region. Again, this is fairly large scale. Now, I'm on sabbatical this year, so one of the things I want to do during my sabbatical is learn something about ground-based gravimetry, and that has been used to try to quantify water storage on a much smaller scale, a small watershed or something like that. So that's one of my objectives during my sabbatical, is to look into some of that. And the idea would be, well, can you take this thing and put it on a truck and drive it around the state and make measurements every once in a while? The MGS does that right now to look for different mineral resources, but they're not using the type of instrument that's needed. And they're using gravimetry, but it's not the same instrument that's used, that's needed for doing this kind of measurement, because it's very sensitive. So I don't know if I answered your question, but I think that, we can start to get to that a little bit better if we can quantify the storage. Again, right now what you would do is you do some kind of a well test to see if, well, I pump here and it causes drawdown here, and it says, well, I can't sustain that pumping rate, and that's going to cause dry up of this wetland.
It seems like this kind of network could give you a pretty good indication of where you're likely to see that. So you would install monitoring wells.
Ideally, yes. I'm hoping that this will help. What we're doing here will help us. Help maybe give some advice about maybe some places where it'd be good to put some more monitoring wells. Tim?
Your model change in storage seemed to be in better agreement with Grace when it was negative compared to positive. Seems to be always biased high. Do you have a hypothesis for that?
Not yet, no. Maybe Jared does, but no, I haven't. We haven't. These are the anomalies that I was talking about. Part of it, is that trying to figure out why. Is the. I mean, you always have to be a little suspicious. Is there something with the processing of the gray signal? Because it's affected by the tides, the position of the moon, all kinds of things affect the gray signal, and so. That's one thing. They've been doing this long enough. You think that probably got all the bugs worked out. So, has
that bias been observed in other sites?
Sure.
Yeah.
Well, I don't know if that particular bias. I think it's a good point that you make that we can look for that. But there have been other studies that are obviously using the same technology. I don't think most other studies have gone into the detail that we've gone into to do the ground-based analysis. So. That's something that those are the things that we're hoping to be able to clear up during this coming year. David?
What are the uncertainties in quantifying the amount of water stored in these different compartments that you've identified. You just presented the numbers, like here's 1,500, here's 20, here's 30.
Right.
But like how accurate are those? How much confidence do we have in those numbers?
Well, I think I feel the best right now about being able to quantify the uncertainties in the lakes. They just seem to be so much easier to work with. The 816 values that we did the regression on, and so we do have estimates of upper and lower bounds on the lake volumes, and they might be 5% or something like that. My recollection. For the groundwater and the salt moisture, I've already indicated for salt moisture, we're just using field capacity. So how good is that? But I wanted to come up with a figure, and obviously it's not very much water to start with compared to the groundwater component. But my objective is when we get done with this project, we'll have all those uncertainties spelled out pretty well. So there's errors in estimating the porosity. There's just errors in the interpolation of the water levels. And we need to figure out how, I don't think it's a simple matter of being able to figure out how to determine what the upper and lower bounds on those estimates will be because of all the different things that go into the calculation. So we haven't come up with numbers on that yet, but it was certainly something that in my proposal that we were going to do that. So right now we come up with what the estimates are for the lake volumes. The groundwater, we still need to work on those uncertainties.
Is this the first attempt of its kind, or do other states have monitoring and knowledge comparable to this already?
I'm not aware. Probably it's easy for me to miss something, but I'm not aware of any state where they've done this kind of detailed analysis for the ground-based data. A lot of states have worked with the GRACE data. It's been used around the world for looking at aquifers under stress and things like that to try to identify where there's overpumping and that sort of thing. And then there have been more recently 1 or 2 studies where models have been compared to the GRACE satellite information, at this gross scale like what I showed, but also using a model like SWAP to compare the SWAP prediction of storage change to the GRACE signal storage change. There was a study done in France recently that was published using the SWAP model on a watershed about the same area as our total study area. So, yeah.
Sure, you talked about the HSPF, and you said the modeling is something that you think has some problems, and then using the same model that it has been calibrated. And it seems like a circular reasoning that I know all that water quality projections are based on HSF. And calibrate for 2-3 years, and then you project it for 10 years, and you're still not sure you are any good. So your use of that model in this thing, how is that going to happen?
Well, I think that we should investigate about the model, and Victor is working on the model. He's just got it started on that. He's been working on it, on and off, but now he's going to be focusing on it during the fall semester and this next year. And already he's been identifying the fact that the ET that's predicted by the HSPF model is lower than the ET that comes from the CETA, which is CBAL, basically simplified energy balance approach that remote sensing. And so the question is, if you calibrate the HSPF model using, a model of ET that underpredicts ET, or if it overpredicts ET, and then you get a good match to the stream flow, well, something's got to give there. So what's going to give? Well, you'll be off on the storage, or maybe you've got your precept wrong. It could be. So we felt that the precip data that we're using in our study, you know, we looked at a couple different products, and the one that we ended up with, we feel is very good. The CETA data, we compared it to eddy flux, and we got very high correlations. Obviously, you don't have a lot of eddy flux locations around in this area, and we're pretty poor on it, but we do have some, and that worked out very well. So we feel pretty good about the CETA data. And then, of course, you have to guess that the streamflow data is you know, pretty accurate. So, and that's a small component of the hydrologic cycle anyway, in general, compared to the precip and the
So people who don't know enough about modeling and all the water quality projections are made, what will be your assessment in terms of telling them, yes, believe in it or don't believe it?
Well, I think it comes down to how much effect does that change difference that, you know, let's say that it is an error in storage, then how much effect does that have on the solute fluxes? Maybe, you know, for certain things it doesn't have much of an effect. If you look at phosphorus, it probably won't have much of an effect. You know, if you're getting the surface runoff okay, maybe it's not. But for nitrate transport through groundwater or something like that, it could have some impact. And of course, transport through phosphorus and nitrate and other elements through lakes and wetlands could be very important just because of residence time. So if you're off on the storage, it could have an effect. I just haven't gotten into that. You know, we're just getting into this model to see how is it that you calibrate. And we know that if you just calibrate to the stream flow, you don't have any other measurements inside the watershed, you're not fully constraining things. So you can come up with, you know, a number of different possible optimal set of parameters to give that result. And by having more measurements, such as storage, you know, maybe we can constrain the model a bit more to get to build a better model.
Moving forward, how do you think you can better estimate velocity?
How is what?
Better estimate velocity.
Porosity? I'll let Jared answer that. He's from USGS, so.
Well, to get broad scale coverage of velocity is challenging. So right now, like the MDS, what we did use, they classified the sufficiency algorithm according to the nature classes. That's what we used. And so at the scale that we're looking at, you know, there's a lot of aggregation that happens to get it to that point. So it's a reasonable approximation. If you wanted to really improve that, you know, there are point estimates of velocity around the state in different very localized studies, but to try to scale that to this size would be a big challenge.
John?
Is the Gray satellite still operational? I got the impression that
No, they haven't. A new one has gone up
it has gone up.
in May of 2018. So that data is becoming available now. And it is a higher resolution, so the tiles are smaller. And actually now you can take the result. I don't know if it's any good or not, but you know, what you saw there was, I don't know, 10,000 square kilometers or something like that is the area of a tile. Let's just say it's 100 kilometer on the side. The downscale trace data for the new, well, you can even do it with the older data. They use some kind of a disaggregation procedure to come up with the downscale data, and they've got it down to 8 miles. I'm sorry using English in this, but they got it down to 8 miles on the side. So you're looking at 64 square mile area for a footprint. That's not the size of the actual footprint, but somehow you're able to downscale that. So if that's true, that really helps us out if those are accurate. So University of Nebraska is generating this and using it for drought mapping and other kinds of things like that. So.
Is there any overlap between the old system and the new one? Ensure that they match.
That I don't know. I don't even think we've looked at any of the new data because we've been focused on this data, and I think the new data is only starting to come out now. So. Yeah, that's something that we definitely want to find out to make sure that they're working properly. It's not like, you know, that SMAP satellite, which is a soil moisture satellite, active, passive well, it would have been great, but that active sensor could put almost as soon as it was put up, so it's only doing passive microwave measurements of soil moisture. If they had had active on, it would have been great. So these kind of things happen, and we'll just have to see whether the new satellite is yielding results that are similar.
All right, thanks a lot, John.
Thank you.
Yeah, you got tired.
We need to shut something.
I'll have to end it.
Yeah, look at the other mix.
No,